Okay, thank you for tuning in. I'm going to talk about recent work to improve LOLA elevation maps for South Pole landing sites, including error estimates and their impact on illumination conditions. I'd like to acknowledge my collaborators on the LOLA team, Erwin Mazzarico and Greg Newman, also at Goddard, and Dave Smith, Maria Zuber, and Jim Head. First, a brief background for those of you unfamiliar with LOLA. LOLA is the Lunar Orbiter Laser Altimeter designed and built at Goddard. It was launched aboard the Lunar Reconnaissance Orbiter just over 11 years ago, and LOLA is one of 7 payload instruments on LRO, all of which are still collecting data in its 4th extended science mission. LOLA is a time-of-flight laser altimeter operating with a firing rate of 28 Hz, and it has a cross-shaped 5-spot footprint on the surface that you see here on the right in the red and green circles. This footprint is canted by about 26 degrees from the long track direction to optimize coverage. Each individual laser spot, shown with the red circles, is about 5 meters wide on the surface at the nominal mapping orbit altitude of 50 kilometers. Most of the time now, LOLA spends as a passive radiometer, conducting photometric studies of the surface, but earlier in the mission, during the nominal mapping phase, it collected nearly 7 billion measurements of surface height, establishing the global lunar geodetic coordinate system with which LRO and other lunar orbiters can align their data. In preparation for sending humans to the South Pole, it's important to have the most detailed and accurate topographic maps possible. These are critical inputs to many aspects of mission design, such as locating subsurface volatiles, mapping traversable terrain, and assessing sun and earth visibility for optimizing power and communications assets. We need to know the topography both outside and within permanently shadowed regions on lander relevant scales of about 1 to 5 meters. Now, imaging-based techniques like stereophotogrammetry and shape from shading face challenges in polar regions due to the extreme shadowing conditions found there. Given their active ranging capabilities, laser altimeters like LOLA can see into the shadows, but gaps between ground tracks and individual laser spots do require interpolation and increased uncertainties in the resulting topographic models. Also, small errors in the LRO orbit reconstruction, typically amounting to a few meters horizontally and half a meter vertically, can cause streaky artifacts in a LOLA digital elevation model, such as the one shown here in the bottom right, at the high resolutions necessary for lander and site planning studies. Estimating and mitigating these issues are 2 of the primary goals of this work. To support Artemis and CLIPS, we worked to revise our LOLA-derived DEMs to quantify their uncertainties and to assess their impacts on the expected illumination conditions. An updated 5 meters per pixel LOLA DEM with uncertainty estimates will be more useful to landing site studies and as a constraint to higher resolution topographic models. The new methodology that we employ is applicable to both polar regions and over wider areas than the small patches that we consider. But as a starting point, we first set on 4 South Pole high priority sites designated as sites Site 1, 4, 7, and 11. And we work on 16 by 16 kilometer areas sampled at 5 meters per pixel. And these areas are shown here in the figure. This figure also shows the average illumination, which is defined as the average visible fraction of the sun's disk. Now, most of the following slides will focus on Site 1, commonly referred to as the connecting ridge between Shackleton and de Gerlache craters. This site has about 2,500 LOLA tracks and about 1 million individual LOLA returns, filling about 10% of all the 5 meter pixels in the 16 by 16 kilometer area. The other sites are similar. Our method is based solely on fitting geolocated LOLA profiles to each other. We use an iterative process in which we estimate 3-dimensional offsets for each track against an independent base map made from 98% of all the other tracks. These 50 batch adjustments are repeated 5 times in total, after which the track adjustments have sufficiently converged. And the orbital geolocation errors are then reduced by over a factor of 10, down to about 10 to 20 centimeters horizontally and a few centimeters vertically. And the typical residual of a single return relative to the base map is about 0.4 meters, which gives us a first estimate of the interpolation error, which is a key quantity that we're interested in. Also, it's important to note that the error covariance matrix is estimated for each track to obtain the formal track offset uncertainties and their correlations. The formal uncertainties, shown by the solid lines here in the figure on the lower right, provide a reasonable estimate of the standard deviation of the actual track offsets, shown by the open circles. This gives us confidence later on when we use the formal uncertainties to model the covariance between the horizontal and vertical components of the orbital errors for each track. Finally, we also remove a small percentage of outliers based on their abnormally high residuals and high slopes relative to local terrain. These are the occasional noise points that make it through the LOLA processing pipeline. Otherwise, they would appear as the occasional flagpole or pothole. Okay, so this slide shows 4x4 kilometer close-ups of Site 1, comparing the old and new DEM on the left and right, respectively. The hillshade in the top row and slope map in the bottom row show how the track adjustment and cleaning process have removed the vast majority of artifacts. Craters are much more clearly delineated in the new DEM, and even some new ones are visible. Simulated images using the new DEM match real images more closely. Here is an example comparing the old and new simulations and a stereo-based model with the real NAC image in the lower right panel. The new DEM resolves craters more consistently than the old one, especially over sloped terrain. Craters below about 100 meters in diameter are still underrepresented due to gaps between tracks. On the other hand, the new DEM doesn't have any artifacts in and around shadows that can appear when using the stereo-based DEM. And here are the full-size new DEMs for all 4 of the sites that we've looked at so far. Now, detailed landing site studies not only require the topography, the surface height here, they also need to know the spatially varying DEM height errors. However, computation of the DEM's full error covariance matrix, which is a 10 million by 10 million non-sparse matrix, would be prohibitive. Instead, we apply a Monte Carlo approach similar to that used in the analysis of the Grail lunar gravity field. We circumvent the infeasible computation of this full error covariance matrix, and instead we use the fractal nature of lunar topography to build a statistical ensemble of 100 clones with similar error properties as the data. With this process, we can, for the first time, estimate the effects of the dominant sources of error in the DEM, namely the interpolation errors, the orbital errors, range errors, and sampling errors. When we look at the whole ensemble of clones, we find that the typical RMS height and slope uncertainties shown in the maps here are about 0.3 to 0.5 meters and about 1.5 to 2.5 degrees. The other thing to note is that interpolation and slope error are spatially correlated with gap size, equivalently the inverse of the LOLA point density. The left-hand figure could be used as a weight map when constraining higher resolution models from imaging-based methods, or as an uncertainty map for solar array height. And the right-hand figure would be valuable in traverse studies, seeking to minimize slope uncertainty along a particular traverse. Now, the other big goal of this effort was to assess the impact of these height uncertainties on the illumination conditions. Our approach is to use the new DEM and its 100 clones to evaluate the statistical spread of illumination condition properties, which are heavily dependent on the local horizon. Conceptually, it's helpful to think of the horizon as composed of a near-field component roughly 100 meters away and a far-field component roughly 100 kilometers away. The clones allow us to estimate the height error and, by extension, the horizon and illumination error. These two figures illustrate how that height error translates to the near-field horizon error. And we see the unwrapped 360-degree horizon at 2 different locations at Site 1. The black line in each figure is the horizon due to near-field topography in the new DEM, and the gray lines are the same for the 100 clones. The big takeaway here is just that the surface height errors translate to near-field horizon elevation errors and variations in the illumination conditions, which we'll see on the next couple of slides. We compute these horizons for the whole map at 2 different heights above the surface, and we examine 3 different figures of merit that are commonly used in the literature: average illumination, longest day, or longest continuous illumination period, and longest night, or longest continuous shadowed period. Here we see the average illumination at Site 1 at 1 and 5 meters above the surface on the left and right columns, respectively. The top row is the average illumination, which, as I said before, is the average visible fraction of the sun's disk, and here it's over the period 2024 and 2025. At each of the 4 sites that we looked at, we identified regions of interest of connected pixels with average illumination over 70% at 1 meter above the surface, with a total area over 2,500 square meters. These regions are shown by the black contours here. They may be targets for a lander or a power cell. Site 1 had the most such regions of interest with the most area satisfying these criteria. To examine the impact of the height errors on the illumination conditions, we performed the same computations on each of the 100 clones independently and examined relevant statistics for the whole ensemble. This is a computationally expensive process and to our knowledge hasn't been done extensively before. So for example, we can map the first percentile of average illumination, shown here in the bottom row. This is equivalent to the minimum of all 100 clones. This gives kind of a conservative lower bound on the illumination that we'd expect at these locations during this time period. In these figures, I've just overlaid the black contours from panel A onto the other panels just to serve as a guide. But if we could look at the contours for the right-hand column, we'd see that at 5 meters above the surface at Site 1, nearly the entire connecting ridge has an average illumination over 70%, even when looking at the first percentile. As noted in previous work, this highlights the dramatic difference in illumination that a few meters of height can make. So it's important to be able to raise a landed asset's solar panels as high as possible. So what are the implications? How is any of this useful? Well, including the impact of the DEM height errors can better bound the range of these key properties. For example, box plots like these of these different metrics can be used to rank the different sites and the regions of interest within each site, with narrower distributions implying smaller uncertainties in the illumination conditions. We find that region of interest 6 at Site 1 generally has the most favorable and least uncertain illumination conditions. At 5 meters above the surface, not shown here, the average illumination and longest night are more similar between the 4 sites that we looked at, but Site 1 still tends to have significantly longer longest day. Okay, so just to wrap up, I hope I've convinced you that detailed and accurate topographic maps are critical inputs to mission and site planning. We've updated the high-res LOLA maps of 4 potential landing sites at the South Pole and demonstrated a method to estimate their uncertainties. Most of the 5-meter pixels are interpolated, but the interpolation errors are quantifiable and manageable. These DEMs have very accurate geodetic control and are unaffected by shadows and are probably the best topography we're going to get anytime soon for the permanently shadowed regions. The height uncertainties do propagate to variations in horizon elevation and predicted illumination conditions, but these uncertainties can actually be used to our advantage by informing landing site studies and figures of merit. Thank you for listening.